Hello, everyone. Welcome to today's coding session. This is a session on data science track. My name is Ajulo Christian. I'm the STEM Programs Manager and a Data Scientist at Hamoye. Thank you very much for joining us to on YouTube and on Zoom here. All right, the topic we'll be dealing on today will be on neural networks modeling. And this will be for the tracking stage for the data science track. So without wasting much of our time, we'll just dive right into the code. So let me share my screen. Okay, waiting for it to load. All right, so I believe you can all see my screen now. Okay. All right, cool. Okay, neural network. The topic will be neural network regression with TensorFlow. So basically, neural networks is a series of, I'm just going to give some preamble theory before we get onto the code. Neural networks is a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. So that's just basically what neural network is. So in this sense, neural network refers to systems of neurons, either organic or artificial in nature. So there are many definitions of regression problem. Basically, in neural network, you can do you have different problems to work with: regression, classification, computer vision, convolutional neural networks, and all that. So, but today we'll be handling a regression problem using neural networks. So, basically, what regression is predicting a number. So, for example, you can predict the selling price of houses, coordinates of a boundary box, or predict the cost of medical insurance and all that. So, a typical architecture of a regression neural network. So there are many different ways to write neural networks, but the following is a generic setup for ingesting a collection of numbers, finding patterns in them, and then attributing some kind of target. So at the end of this session, I can try to share the notebook or not. So, but let's just follow along first. So, let's move on. So the architecture, so we have the hyperparameter typical value. So in the architecture of a regression network, we have the input layer, the hidden layer, the neurons per hidden layer, the output layer, the hidden activation, the output activation, the loss function, and the optimizer. So the input layer is same shape as number of features. For example, if you are dealing with working on house price prediction, so the input layers might be the bedrooms, the bathrooms, car spaces, and all that. Then the hidden layers might be problem specific. The neurons also problem specific, generally from 10 to 100. So this is just like a basic typical architecture of a regression neural network. As I'm explaining, I'm trying to give a brief explanation of each. For you to grasp, like I always say, to have a good understanding, you should always go back and check on them. So for the hidden activation, we have the ReLU, which is the rectified linear unit, the attribute activation, none, or ReLU, or logistics. Then the loss function, that's the normal regression loss function, we have the mean squared error, mean absolute error, mean squared error, and all that. So for the optimizers, there too, we have the stochastic gradient descent and the adder. So I'm just giving a brief preamble for this architecture. Once you start coding, you get to see them and understand. So this was gotten from hands-on machine learning with scikit-learn by Aurelian Jerome. So you can go back and understand. So getting onto the code, I'm going to import TensorFlow as TF, then getting to know the version I'm using. Currently, I'm working on my Google Colab notebook. Okay, so for that to load, it's not supposed to take time. In loading. Okay, so after importing my TensorFlow as TF, since we are working on a regression problem, to just begin, like before we get to work on real life data, I just want to create some dummy data, just like a linear data, to explain some of the concepts before we get on working with real life data. So what this code is doing, I imported my libraries. I'm just creating an array of features, a linear data, X and Y. Then it's just a linear data we're working with before we get to real life data. So in regression, we have the regression input shapes and output shapes. So one of the important concepts when working with neural networks are the inputs and the output shapes. So the input shape is the shape of your data that goes into the model. The output shape is the shape of your data you want to come out of your model. So this will differ depending on the problem you are working on. So neural networks accept numbers and attribute numbers. These numbers are typically represented as tensors or arrays. So this image can just do justice to what I was trying to explain. So, like I said, the input shape, for example, you are predicting house, your prices of house. These are the input shape represented in tensors. For example, the bedroom, the bathroom, the garage, it's represented in tensors. Then input it into the machine learning algorithm. It's going to output a single shape, which is the price of the house. So it's just like a simple breakdown of what I was saying. So if you're working on building a machine learning algorithm, your inputs may be number of bedrooms, number of bathrooms, number of garages, and all that. So then at the end of the day, your output will be a single shape that you're predicting the price, the amount. So steps in modeling with TensorFlow. First of all, you're creating a model by piecing together the layers of the neural networks. Then someone is asking, no, there's not an form for this session, this is a code session. Then, or import a previously built model. So they are functional or sequential API. Then next step is compile the model. So you define a model performance, defining how a model performance should be measured, as well as defining how it should improve. That's the optimizer. The next step is fitting a model, letting the model try to find patterns in the data. So let's do some action using the Keras sequential API. You can go back and in documentation in TensorFlow to know more about the Keras sequential API. So we'll be using it to build the model for our regression data. So as usual, I've already written down the code. I will explain because of time. So first off, you set a random seed, I've set it to 42. Create a model using the sequential API. If you go back to the documentation of Keras sequential API, when creating a model using the Keras pf.keras.sequential, then I'm putting just a single layer now, .dent one. Then to compile the model, I'm using a loss function, which is mean absolute error for my loss function. And for the optimizer, I'm using SGD. So this is just like a simple neural network model. And afterwards, I will fit the model and run it for 5 epochs, meaning I run it for 5, reiterate it 5 times. That's what this code is just doing. So let's run this here. So we fit the data. So let's just check our X and Y data we formed before. So using the dummy data, let's make predictions on that data. So if you notice, for my predictions, I want to predict the 17th number from my normal linear model. If you remember, I'm working with a dummy data, which is this linear model. That's for the S. If X is 14, Y should be 24. So, but I wanted to predict if X would be 17, what what would Y give me? So, but for here, it gave me 22 as the answer. So normally it's supposed to give me 17 based on my dummy data. I created the linear format of data. So it's supposed to give me like something close to 27. So this model is not predicting very well. So the next step to do is to improve the model. Mind you, I'm working with the dummy data. When we get to work with real life data, you understand better. So improving the model, to improve a model, you alter most of the parts. When creating a model, you want to add more layers, increase the number of hidden units. Then when you're compiling the model, you can change the learning rate of the optimization function. When you're fitting the model, you can fit the model for more epochs. That's leave it to train for longer. But this will just run 5 epochs. So that's what it means. So but let me just show you this picture to have an understanding. So what the picture is doing, to explain better, to improve your model, this is a smaller model, and this is like a bigger model. So common ways of improving your model, adding layers. This is this blue function here. So if you can see my screen clearly, when you're adding layers, this is the part you're adding layers. For this simple model, I just add 3 layers here, and this is like 5 layers, so it's more to improve the model. Sometimes you can do is increase the number of hidden units. When increasing the number of hidden units, which is this green function here, sorry, this, whatever this color is, the hidden unit, which is this 100 there. And you can change the activation function to have ReLU, HGD, or softmax. Then you can change the optimization function, which is using this Adam here. For this other smaller model, it was still Adam, but you can still change your optimization function. If you go back to documentation, understand better. Then you can change the learning rate. This model learning rate was the 0.001, but here it was 0.001. So these are ways of improving your model by working or tweaking on some hyperparameters. Then you can fit on more data. Of course, you can get more data, then you can fit for longer, which is the input here. So if you can see my screen clearly, you understand better. So moving on, let's see how we can improve our previous model. So let's run this code again. The previous one we trained for just 5 epochs. So now I'm going to train for 100 epochs, not 10. So that's the difference of previous model. All right, that is done. So let's just see what X and Y looks like. So let's predict the 17th number of X. So now we have 29. So this is quite better because for my model here, when X was 14, Y was 24. So predicting if S should be 17, it should be 27 thereabout. So our model is predicting 29, so it's not bad. So moving on to evaluate the model. Typical workflow you go through when building a neural network is you build the model, you evaluate it, you build the model again by tweaking it, you evaluate again, you build the model by tweaking the parameters, you evaluate again. So just like a typical workflow for building a neural network. Then you can also visualize the data to understand how the model is performing. So still working with dummy data, I want to create a bigger data set before we get to work on the real life data. So making the labels for the data sets that adhering to the same pattern as before for our Y, creating a Y data. So let's check the length. Length of our data should be 50. Okay. So now I want to split our data into train and test set. So I'm working with the first 40 examples, which is 80%, and the last 10 examples, which is 20% for my X and Y train. So now plotting a visualization to understand how my data is. I'm going to plot a scatter plot representing the X ray and Y train, and a scatter plot representing the X test and Y test, which is our test data. Then we view it. Okay, this is our data. The training data is in the one in the blue color. The testing data is this green color. So for now, with this visual, we understand what our training and testing data looks like. So when we run the model, we'll see how the model is predicting. I also visualize it so you understand. So using the model as before, but this time around using 100 approach, thereby creating just one layer here, dense input shape 1, optimizer, SGD, metrics by using mean absolute error, then fitting the data. Then there's something you can do to check your model summary to see what's involved in your neural network model. So it's called summary. You can do model.summary. So here we'll see that we are using the name of the model is sequential 2. The layer is dense 2, just 1. Output shape is 1. Parameters are 2, which is this optimizer and loss here. So let's make some predictions. Mind if you have any questions, just drop it in the chat box. As I'm going, I'll try to answer, or after the session, I'll answer the question. So let's view our predictions. So plotting a visual to see how our model was performing. That's by creating a function to plot our data. So let's see how it performs. So if you notice, this is our data, the training and test data. So these are our predictions. This model is not too bad. It's not far from our predictions. Normally, a perf red dot, we should overlap these green dots. That should be like a good perfect model. But this two is still performing better. That's not bad. So to evaluate our predictions, can use mean absolute error or mean squared error. By now, you know the definition of both. So the lower each of these values, the better. You can also use model.evaluate, which will return the loss of the model as well as any metric setup during the compile. So that's another way you can use it in TensorFlow, model.evaluate. So let's just use model.evaluate. Based on in the model, the default metric that there was mean absolute error. So then calculating the mean, okay, waiting for that to load. Okay, I think my network is slow. In the mean squared error here, let's wait for that to load. Was 223. So instead of typing this, I'm just going to create a function for my mean absolute error and mean squared error, so that when we get to work with a larger example, I'll just call the function. Okay, so working with a larger example, what we just worked with previously was a dummy data equation. So now I'm going to work with a real-life data set. It's the data we used previously, the medical insurance data. So since we've seen the fundamentals of building neural network regression models in TensorFlow, those are just the fundamentals I did working with the dummy data. So now working with real-life data, you just get to see how it works. So more specifically, we're going to try to predict the cost of medical insurance for individuals based on a number of different parameters from the data sets. So I've got this data set from Cargo. So just importing my necessary libraries I need to run, reading the data, checking, viewing the data. All right, so this is the data. We have the age, the sex, the BMI, and all that. And turn all categories into numbers. Basically, this data, like we all know with machine learning, it doesn't work with categorical numbers. You have to categorical data. You have to change it to numbers. So I'm going to preprocess it using pd.getDummies to turn the categorical columns into numerical columns. So yes, that's what this code is doing. So with pd.getDummies, it will create a separate column for each of these categorical data, turn it into numbers. Then splitting our data into X and Y. Our target column is these charges. So that would be our Y column. The S would be everything except charges column. So we already know this. So viewing data, creating our train test split using a test size of 20% and a random state of 42. Then creating a model. We'll be using the same model as previously. So this time around, we have two layers here. Tables of characters of layers dense 1, tables of characters layers dense 2, using a loss of mean absolute error, using an optimizer of HGD, then fit and train the data. Then, so waiting for this to load. All right, so we fit the data for 100 inputs. Let's see how it's moving. So after evaluating the model, mind you, if you remember, like I said, if you are working with mean absolute error or mean squared error, the lesser the mean absolute error, the better a model. So with this, you know that our model is not performing good. The mean absolute error is 7280, so that's quite large. So we can try 3 different things. We can increase the number of layers from 2 to 3. We can increase the number of units in each layer, except for the aspect layer. Then we can change the optimizer from HGD to Adam. So if you remember, this was the architecture of a neural network regression problem, like I said in the beginning. So we can just tweak those in our model to see if it will perform better. So now I added an extra layer and increased the number of units. So the extra layer I added, the first time, if you notice, it was dense 1 and dense 1. So I added it to dense 100 units, dense 10, and dense 1, important for the output layer. So I'll get to your question after the session. Okay, asking a question if I can explain the results of the insurance model, if it's overfitting. So for this after I evaluated the model, this first one, if you notice, yeah, it's basically kind of like overfitting, you can say that, but with this mean absolute error, it's too large. So if you understand the metrics when evaluating your model, mean absolute error, the lesser the amount of your mean absolute error, the better your model. So with this, I can say it's overfitting. Yeah, you can say that. So, or underfitting, whichever. Okay, cool. But when I move on, you understand why I said, okay, this mean absolute error is too large. So just try and follow along. You have an understanding of it. So I'm trying to tweak the model now to see if I can reduce my mean absolute error and also if I can do it with a lesser training time. So that's my target now. So I added extra layers. I changed my optimizers from HGD to Adam, and I'm fitting for 100 inputs. So let's run this model again. It's the same as the other, just that I added an extra layer and I changed the optimizers to Adam. Okay, then evaluate the model. And this would reduce the mean absolute error. If you notice, it's reduced the mean absolute error for over like 3,000 units. Previously, it was 7,000. Now it's like 4,800. So at least when you tweak the model by adding extra layers and changing the optimizer, it's performed better with this. So another way to get an understanding of your data, if you plot what we call the loss curve, that's plotting the history. So I'm going to plot the loss curve using this code, pd.data frame, the history. So in this loss curve visual, this red is the mean absolute error, sorry, whatever this color is. Then the blue is the loss. So if you notice, it's like they are intertwining each other. That's why you're not seeing the loss part, which is supposed to be this blue. So from this, it looks like our model loss and the main, they're both decreasing. So here, they are of the same lines in the plot, so they overlap each other. So from here, it has been reducing, and reduce better. So this is like a good performing model. You can also still improve this model by still tweaking some parts in the model. So moving on, this tells us that the loss might go down if we try to train it for longer time, if we try to add more layers, or if we try to add more data. But for now, there's a question that we can say, okay, how long should we train it for? It depends on the kind of problem you are working on. Sometimes training won't take very long. Other times it will take longer than expected. So a common method is to set your model training for a very long time. E.g., you can get up to thousands of inputs, yeah, but set it up with what we call early stopping callback. So that, for example, if you are training for like a longer time and the model improves but stops improving for some time, this early stopping callback function would automatically stop the model when it stops improving, so that you won't be training for longer. For example, you are training for 1,000 inputs and at 600 it improves, getting to 700 did not improve, getting to 800 is still not improving. So the early stopping callback would automatically stop it when it's not improving better. So that's just a function of an early stopping callback. Okay, so I want to try and train our model for a little more longer using 100 inputs. Before we used, how many inputs did we use? Okay, then evaluate the model trained for 200 total inputs. So if you notice, it's also reduced than the former one we had here, which is 4,000. This is 3,000 now, after training for like 200 inputs. So let's plot it to see if our loss function reduced or not. So this is another way of understanding a model visualization too. You can create visuals of a model too. Instead of, if you don't understand numbers perfectly, you can understand with the visual. So if you notice also, they are still like overlapping too. So this model improved by training for longer, 200 inputs, and increasing the layers and adding your changing the optimizer from SGD to Adam. So these concepts, you can always go back and understand the architecture of the neural networks. Each of these hyperparameters that you can tweak or what you can do for your specific problem you're working with. Okay, there's a question here from Carl. He said, what's the difference of training longer? Of course, it was the same approach. No, I trained for 200, not 100. If you notice here, I said people should only show the 100 since we've already the history available. I did history too. First of all, we trained for 100, but this time around I trained for 200. But using this history, if you notice, the first model was insurance model 1, and this is insurance model 2. The loss. So I overread the approach. So I started training from 100 down to 200. So that's why you see that it's 100 approach. So I just overread the first approach. Since my previous model was insurance model 1, so I'm using insurance model 2. From where that one stops, I'm training more from 100 to 200. I don't know if you understand. So if you understand, I'm overriding it from the previous model that was trained for 100. I am training for extra 100 approach on top. That's what I mean. Okay, lovely. So do you understand now? Okay, cool. All right. Moving on, there another way of improving your model, what we call pre-processing the data. This first time, what I did with this first model, I'm going to show you the difference. I just let's go back. I just did what we call PD.get dummies. I did not do what we call normalization or standardization. So in neural networks, let me just go back if I understand. Let me go back to what I want to do now. All right, so preprocessing data, normalization and standardization. A common practice when working with neural network is to make sure all the data you pass to them is in the range of 0 to 1. So this practice is called normalization. So scaling all your values from their original 100,000 to be between 0 and 1. This is called scaling normalization. So in the data sets we worked with, some of the data range were from 0 to like 100 or 0 to like 200 and all that. So I didn't normalize it. I just one-hot encoded the categorical data to numbers. So normalization is done by subtracting the minimum value and then dividing by the minimum value minus the minimum. I don't know if you understand. Let me see it again. This is done by subtracting the minimum value, then dividing by the minimum value minus the minimum. That is just English. You get to see it when we run the code. It's called min max scaling. So there's another process called the standardization, which converts all of your data to unit variance and 0. So this is done by subtracting the mean value from the target feature and then dividing it by the standard deviation. So these are just English and grammar. So let's just get on to the code. You understand what I mean by min max scaling and also standardization. You should also know this because we've done regression problem before. So that was in stage B or so. Yeah. So we handled normalization and standardization then. So I'm going to read the data again this time around instead of just changing the categorical data into numerical data. I'm going to normalize it. So let's just check out the data. It has categorical and numerical data. So what I'm going to use to one-hot encode and normalize data, I'm going to use some few classes from scikit-learn library, something called the make column transformer. This will be used to build a multi-step data preprocessing function for my min-max scaler and for my one-hot encoder. So there's a library called make column transformer. It's a class in scikit-learn library. So you can go back and get an understanding of that. So this code here, let me just explain what it's doing. I'm going to import the make column transformer, and I'm going to import the min-max scaler and our one-hot encoder. This min-max scaler is what is going to normalize the data. So I'll create a column transformer. This will help us normalize and pre-process our data like a pipeline. So this code here is doing 6 is equals to make column transformer. Inside the make column transformer, I'm passing the min-max scaler. And the min-max scaler, I'm going to pass the columns age, BMI, and children from our data, which is the age, BMI, and children from our data. I'm trying to reduce these numbers from 0 to 1 instead of 19, 28, and 0, so that the ranges will be from 0 to 1 instead of this amount of number. So that's what this min-max scaler will be doing. Then the one hot encoder is going to encode the categorical data into numerical data, turning them into tensors. So then this creating my X and Y data, target data is the charges. So you already know that. Creating my S train and Y train, S test and Y test. Then I'll fit my data using this column transformer, first of all. Then I'll transform the training and test data with normalization, which is the min-max scaler. So this function here, this CT, is a function like pipeline that's going to scale it, normalize the data, and also preprocess data, categorical data into numerical data. So that's what this code here is doing. So let me just run the code. That's done. So let's view our S train. This is the S train that wasn't normalized and the one that wasn't encoded. So you can see showing the categorical data and the other data that were not normalized. So then the S train normal will be an example of S train that was normalized and encoded. So if you notice, this one here is representing this age that was 19. Now it's normalized it to a range of 0.6. So the essence of normalizing your data is to reduce it from a large number that is from probably 0 to like 100,000 or whatever to within a range of 0 to 1. That's what normalization is all about. All right, so moving on. So if you notice the normalized one hot, the coda shape is larger because of the extra columns and all. So using the same model as before that gave us a mean absolute error of like 3,000 plus. Let's just pass the model on to this our new normalized data, and let's see how it will perform. Mind you, you will not be seeing this the learning rate, because I did something called verbose equals to 0. So this will not show the output. That's the essence of this verbose. So this model has trained. So let's evaluate the model on our normalized test set. So if you notice, it's reduced to a mean absolute error of like 3,172. With this same model on our data that was not normalized, the value was 3,900 or so. So if you notice, because you normalize the data, you will have better performance model. You can also do those other tweaks like say by adding layers, changing the learning rate, changing the optimizers and all that. So these are the ways of tweaking your model to have a good performing neural network model. So now finally, let's compare the results from insurance model 2 trained on non-normalized data and insurance model 3 trained on normalized data. So if you view both of them, you see that the new model should perform better. That's when we got this 3,172 mean absolute error. Like I said, you can also tweak the model to perform better. So if you notice, this was 3,499. The new model on normalized data is 3,172. So the essence of all this is to have a good performing model, and also or a push. The essence of machine learning engineering is that, okay, you want to have a good performing model with less time. So it doesn't necessarily mean that you train for longer time. So there are other things you can tweak in your model so that as you're training for that particular time, you tweak other parts in your model or your data, you get a good performing model. So that brings us to our session for today. So these are just like a brief intro of how a neural network modeling works. So mind you, worked on a neural network regression problem. That's what we were working on so far. So I hope you've gotten a grasp of the concepts and all. If you have any question, drop it in the chat box. and I'll reply. During the course of the session, I've already replied some of the questions dropped. So, okay, there's a question from Joseph saying, I'm not able to use placeholder function in TensorFlow 2, and I can't seem to be able to install TensorFlow 1 and Google Colab, please. Well, there's a way for you to install or use TensorFlow 1.15 in Colab. If you check, just browse on the particular code on how you can use that. In the code snippet too, there's a function on how you can, instead of using TensorFlow 2, you can use TensorFlow 1.5 using your placeholder function. It's there in the documentation. You see it's possible, you can use it. So Joseph, just go back and understand how to do that. Check the documentation, you see how to use it and Colab on anywhere you can use it. So any other question? Okay, there's a new question. You say, may you know why Adam works but not HDD at the larger data set? Okay. If you check how do I explain it, okay, I can give you to go back and do your research, but let me just give you a short answer. Why Adam works better than the HDD? It's just like another example. Okay, let me just show you something. For the activation function, there's something that's called the ReLU. It is known widely that when you're using ReLU, your model will perform better than using other optimization, learning rate. So for Adam performs better than the HGD for this particular data set. It is also there in documentation of both optimizers. I'll just leave you with that answer now, but for you to have more understanding, I'll tell you to go and do the research so you see why Adam performed better than HGD. So I'll leave you to do that. You see the finding, you see the reason there. So to satisfy your curiosity, so just go back and check which of the optimizers will perform better for your larger data set or your small data set. So just go and check it. There are other optimizers you can use. Let me go back to my architecture so you see what I wrote. So there's the HGD, there's the Adam, there are more too. Then for the output activation, there's the ReLU, the logistic. And if you notice for my model here, I didn't use an output activation. So if I have used an output activation for the ReLU, you will see my model would have performed better. So I just did a breakdown of an introductory part of how you understand neural networks, how you build a neural network model. So I guess I've answered your question. Who asked that question? I guess I've answered your question. All right, any other question? Let me stop sharing my screen for now. Any other question? Have time for one or two more questions before we call it a day. Okay, cool. You got an understanding. All right, so in the absence of no further question, I guess you've gotten a good understanding of a brief introduction of how neural networks work. Mind you, there are different applications of the neural networks. I just worked on a regression problem. You can work on a classification problem. You can work on a computer vision problem. You can work on different problems in neural networks. So it's just for you to know what you want to do or the particular project you want to work on or the problem you want to solve. Yes, you asking about the notebook, it will be shared on Slack, but I'm not making any promises, but you definitely get it probably on the Slack channel or not. So, but as usual, you can always come back to our YouTube channel. The video is there on our YouTube channel, I'm a YouTube channel, I'm a HQ. So you see this particular video. If you don't get to see the notebook, you can always go back to this video on our YouTube channel. So, and okay, that's okay, no other question. Okay, there's a final question before we call it a day. If we are going to work on classification, we can follow the same procedure. Yes, there's a standard, like I said, there's a standard architecture of a neural network. There's a standard procedure. The procedure I just followed is called the Keras sequential API. I don't know if you joined from the beginning. This procedure I used was the Keras sequential API procedure using TensorFlow. The other ones you can use PyTorch, and there's PyTorch, there's TensorFlow. So for TensorFlow, using the Keras sequential API methods, you can follow the same procedure, but you can tweak some other architecture in it. That's why it is specific to the problem you want to solve. If you are solving a computer vision or a regression problem or a classification problem, so they all have the set down rules and procedure to follow. Apart from the Keras sequential API procedure, there are other procedures. Just go on TensorFlow. Quicker way to access it is using this collab. You see the different documentations and different procedures and architecture to follow. So I guess I've answered the question, Tolulokbe. All right. So, okay, cool. Any other question before we round off today's session? And mind you, for this stage in those in the data science track, after the quiz, you're working with a tag along project, which is satellite image data. So on the platform, you should know what you need to do and what you need to submit and all that. So the information is there for you. So wish you good luck in your learning progress and your quiz and your tag along project. So in the absence of no question, I guess I have to call it a day. Thank you everybody for joining and have a lovely day ahead. See you next time. Bye for now.